Hi and welcome to ExtraSci. This is Life Sciences grade 10. So in this video, we're going to be looking at organic compounds. So organic compounds are the products of living organisms. They contain mostly the CHON elements. Sometimes they contain phosphorus, calcium and sulfur. So what are the CHON elements? As you can see, the word is CHON. These are called CHON elements. C is for carbon, H is for hydrogen, O is for oxygen, and N is for nitrogen. So example of organic compounds include carbohydrates, lipids, protein, nucleic acid, and vitamins. So these are the examples of organic compounds that we are going to be looking in more details. So carbohydrates. Carbohydrates are made up of elements carbon, hydrogen, and oxygen. And the ratio of hydrogen atoms to oxygen atoms is always 2:1. So this means if there are two hydrogens, there are always going to be a single oxygen. This means 4 hydrogens equals 2 oxygens. Carbohydrates are initially made by plants in the form of glucose from water and carbon dioxide during photosynthesis. We're going to look more into photosynthesis in the coming chapters. So carbohydrates are divided into 3 groups according to the number of saccharides they contain. So what is a saccharide? Saccharide is the same as sugar. So the 3rd division is monosaccharides, which means 1 sugar molecule, and then disaccharides is 2 sugar molecules, and then polysaccharides is many sugar molecules. Mono is 1, di is 2, and poly is many, and saccharides means sugar. The mono and disaccharides taste sweet and are soluble in water, while polysaccharides are not soluble in water and they do not taste sweet. So this is an example of monosaccharides. Like I said, it's a single sugar, and right there is the chemical formula C6H12 and O2. As you can see there, if there are 12 hydrogens, there are 6 oxygen, 2:1. Remember that. Always remember that ratio. There are 3 types of monosaccharides. These is glucose, fructose, and galactose. Glucose is the most basic monosaccharide for carbohydrate. It makes most of the polysaccharides that you see. Like in every polysaccharides, there will be glucose. In disaccharides, there will be glucose. So here is disaccharides, which is a double sugar. Like you can see there, it's C12, H22, and O11. Now see, hydrogen is 22 hydrogens equals 11 oxygen. Ratio is 2:1. And you can see there the glycosidic bond. Joining 2 monosaccharides produce a disaccharide and a water molecule. This is an example of a condensation reaction. A condensation reaction is where water is one of the products. You will talk about this in chemistry. So these 2 monosaccharides are joined by a glycosidic bond. A condensation reaction, like I said there, is a reaction where water is one of the products. There are 3 types of disaccharides. This is maltose, sucrose, and lactose. Now, see there, I said that glucose is the most basic monomer for carbohydrates, and we said monomers were building blocks. Now look at that. Maltose is glucose and glucose. So joining 2 glucose produce sucrose. Produce maltose. And sucrose is glucose and fructose. The second monosaccharide, fructose. Now, when glucose is joined with glucose, you get maltose. When glucose is joined with fructose, you get sucrose. And when glucose is joined with galactose, you get lactose. So there is glucose, and then there is one of the other 2 monosaccharides, and then you get a disaccharide, and then a polysaccharide. As you can see there, many sugar molecules. It's C6H10O5. Again, even if it's a polysaccharide, the ratio of hydrogen to oxygen is always going to be 2:1. I don't care how many molecules of sugar do you have, but the ratio of hydrogen to oxygen, if it's a carbohydrate, is going to be 2:1. Joining more than 2 monosaccharides produces a polysaccharide. Now there are 3 types of polysaccharide. There's starch, there's glycogen, and then there's cellulose. Starch is found in plants. Glycogen is found in animals, and cellulose is also found in plants, but not as a storage molecule, because starch and glucose are storage molecule, while cellulose is a structural molecule. These are not important. So here are the uses of carbohydrates. Carbohydrates are a source of energy. Energy is released from glucose during respiration. Respiration is when you are breaking down carbohydrates, and you are expelling carbon dioxide. Carbohydrates also store energy as starch and glycogen, which can be converted into glucose. Carbohydrates are also structural components. Cellulose in plant, like I said, starch and glucose are storage molecules, while cellulose is a structural components in plants. Now this is a test for carbohydrates. To test for carbohydrates, you need to use the Benedict solution. This test for the presence of glucose, cellulose, and maltose. Here we are searching for if there is a presence of carbohydrate. Now you will mix the sample of Benedict solution and boil the mixture in a water bath. There should be a color change. Simple sugars reduce Benedict solution to a red precipitate of copper oxide. Now if there is no simple sugar, the solution will remain blue. Iodine solution is used to test for the presence of starch. In the presence of starch, the iodine solution will change color from brown to blue-black. If there is no starch, the solution will remain brown. Here an example here is a test of presence of starch. See, a potato obviously has starch, and then you peel it and then you just drop a few iodine, and there you see a color change there to blue to dark blue. Now let's get into lipids. Now lipids are also made of carbon, hydrogen, and oxygen, but now the ratio of hydrogen to atom is no longer 2:1. Of hydrogen atoms to oxygen atoms is no longer 2:1. Now lipids are have more than double the number of hydrogen atoms than oxygen atoms. They are made of glycerol and fatty acids. One lipid molecule consists of 1 glycerol molecule and 3 fatty acids molecule. Right there is an example of a lipid. You can see here, this is 1, 2, 3 fatty acid molecule, and that right there is a glycerol. So glycerol and 3 fatty acid molecules make up 1 lipid molecule. So properties of lipids are insoluble in water. This means they do not dissolve in water. They are soluble in ether and alcohol. They do, however, dissolve in alcohol. They are hydrophobic. This means they are water repelling. Hydrophobic, phobia, and then hydro means water, phobic means phobia. They are water repelling. Lipids are further distinguished from each other as being either saturated or unsaturated. Saturated lipids are derived from animal and they are solid at room temperature, while examples include butter and lard. And saturated lipids have single bonds in their fatty acid structures. I don't know, see, here's an example here. This is the example of saturated and unsaturated. Like you can see, a saturated fatty acid. Now this is not a lipid, this is a fatty acid. A saturated fatty acid has single bonds here. Single bond, single bond, single bond, single bond, single bond, single bond. These are all single bonds. You will learn about this structural representation of in chemistry, where you are going to be using these lines, and then double, where you have double bond, you have two lines. This means a double bond, and this is polyunsaturated. So obviously this is an unsaturated fatty acid. It will make an unsaturated lipid. And here you have 1, 2 polyunsaturated fatty acid. So this is the difference. This is saturated. These two are both unsaturated. They have double bonds. Unsaturated lipids are mainly derived from plants and they are liquid at room temperature. So if a lipid is unsaturated, it's going to be liquid at room temperature. Example include olive oil, canola oil, and sunflower oil. These are all unsaturated lipids. They have single bonds in their fatty acid structure, like we've just seen here. Single bonds in their fatty acid Unsaturated lipids have single double bonds. Single double bonds in their fatty acid structures. This here is a single double bond, which makes it unsaturated. And then lipids are energy reserve initially made by plants from excess carbohydrates. So lipids are initially made by plants from excess carbohydrates. When you are storing carbohydrates, you end up making lipids. They are stored by plants in seeds and fruits as unsaturated lipids. Animals get lipids from plants through feeding, and they convert plant lipids into saturated fat. Now, so they take the unsaturated lipids and then they make it saturated lipids. Animals store this saturated fat underneath the skin as fat adipose tissue. Animals also use saturated fat to synthesize cholesterol. Now, what is cholesterol? Cholesterol is a wax-like substance that forms part of the cell membrane and hormones. Excess intake of saturated fat obviously will lead to a high cholesterol level in blood. Since we said animal will take this fatty acid and then they will make cholesterol. This is a problem. You don't need to have a high cholesterol level in your blood. This leads to a disease called atherosclerosis. This is the narrowing of the arteries due to the deposition of fat in the arteries as a result of high cholesterol level. And then obviously this will lead to blood clotting and eventually a heart attack, since this cholesterol is going to keep on blocking the blood, and then it will clot. Now, importance of lipids in animal and plants. Lipids, they can be used as source for reserved energy. So the breaking down of fatty acid releases a large amount of energy. This is called the beta oxidation of fatty acid. Insulating material. Fats are non-polar molecule, and thus they cannot conduct heat. Since they are non-polar, they cannot conduct heat. This allows marine mammals to insulate their body heat from the cold seawater. Fatty acid can also be used as shock absorption. Remember, fats from a layer that surround organs of the body and protect them from mechanical injuries. So you need fat for shock absorption. This is for protection, but you don't need it. You don't need it to be there in large quantities. Lipids can also be used as structural components of cell membrane. They can also be used for waterproofing. They can also be used for the absorption of vitamins. They can also be used as source of water. You can pause here and just go through these. Now, test for lipids. To test for lipids, you need either a filter paper. You need ether and filter paper. So what you'll do is you grind the test material, transfer it to a test tube, add ether and all the reaction and allow, this should be allow here. This is not all, this is allow. Allow the reaction to take place for approximately half an hour. Filter the solution and drop the filter to a clean filter paper. If the test material has lipids, a greasy spot will form on the filter paper after the drop has evaporated. Now, proteins. Proteins are polymers. Now, what is a polymer? Meaning they are large molecules made up of many small molecules. You can argue and say carbohydrates are polymers, but then carbohydrates are divided into three. There is a monosaccharide, a disaccharide, and then a polysaccharide. Obviously, a polysaccharide is a polymer. It's a large molecule made up of small molecules. These molecules are called monomers. Monomers are the building blocks of polymers. The building blocks of proteins are amino acid. So amino acid are the monomers for proteins. Amino acid are also made up of the element carbon, hydrogen, and oxygen. But in addition, amino acids have nitrogen, and some have phosphorus, sulfur, and iron. All amino acids have nitrogen. There are 20 different amino acids known to science so far. And here, excuse that, the sequence at which the amino acids are connected to each other to make up the protein and the type of the amino acid connected determine the type of protein. A single amino acid can be sometimes called a peptide. Now, this is important here. What is important here is you have amino acid. and the sequence at which they are connected would determine the type of protein. And the type of amino acid that are connected would determine the type of protein. This is why we have 20 amino acids but lots and lots of proteins. 2 amino acids connect to each other either by a peptide bond to make up a dipeptide. So 2 amino acids connected to each other make up a dipeptide. This connection is through a peptide bond. And 3 amino acids connected to each other make up a tripeptide. So there's 1 amino acid called a peptide, and then there are 2 amino acids connected by a peptide bond to make up a dipeptide, and then there are 3 amino acids connected to each other to make up a tripeptide. A long chain of amino acid makes up a polypeptide. So there's peptide, dipeptide, tripeptide, and then a polypeptide. Now a protein is a product of polypeptides connected by many peptide bonds. So then a polypeptide will then make up a protein. Polypeptide chain can fold and form loops onto themselves. Now this is where we start differentiating between proteins. These fold and loops determine the function of the protein. Like I said, proteins are very sensitive to temperature and pH, and they lose shape and function at high temperature and extreme pH.